Hello everyone, my name is Asad. I'm a graduate student at Mountain State University in the Computer Science department. Today I'm going to talk about our paper, Evolutionary Grain Mixing to Improve Profitability in Farming Winter Wheat. My co-author is my academic advisor Dr. John Sheppard. So protein content in wheat plays the most important role in determining the price of wheat production. It is affected by several environmental factors like temperature, soil nitrogen level, genetics, timings, and precipitation. And due to this variation, the protein content in wheat changes not only from year to year, but also from crop to crop. Today, the device for tracking protein content in wheat is available, but it is expensive, thus making it inaccessible to several small farmers. Therefore, most of the wheat producer take their harvest to the nearest elevator and collect whatever amount is paid to them. So for this paper, our proposition is to mix different quality wheat to change the average protein content and to find the optimal mixing plan that balances both cost and profit. More formally, the problem statement can be defined as determining the optimal mix of wheat from storage bins to maximize profit when sold to a set of elevators. Finally, our goal is to investigate if mixing grain increases the profitability of the farmers and if the increased profit is sufficient to invest in the protein tracking infrastructure. This slides provides an example of the grain mixing problem, like how it can be beneficial to improve the overall profit. Sorry, just a second. Can you see my laser pointer?
Not the laser pointer, but we can anyway see your mouse, so I think it's okay anyway.
Oh, okay, okay. So usually the farmers after the harvesting season store their wheat in multiple bins, and from each bin they load trucks in batches and go to the nearest elevator to sell them. So in this example, we have 3 bins with different amount of bushels and protein level in each of them. And the table here shows the elevator prices for different protein requirements. Now, if we were to load trucks individually from each bin, we would get a price of $850. However, if we mix grain as shown in this picture and load different trucks that change the average protein level, it can give us a price of $1,000 that increases the profit by $150. And if we see track 1 in here, which mixes grain from bin 1 and bin 2, actually pushes the protein level of bin 1 to the next grade and keeping the bin 2 in the same grade, so which basically provides the scope for optimization. And there are 2 costs associated with wheat distribution. One is the mixing cost and another one is the delivery cost. Mixing grain from bin incurs a mixing cost that depends on the mixing difficulty. So usually the beans are distributed across multiple sites. And based on the distance between the sites, the mixing difficulty varies. So this figure here shows that mixing beans from the same site has a lower difficulty level than mixing beans from other sites. And the table here shows the cost for different mixing difficulties. The delivery cost also is not constant and depends on the distance between sites and elevators. The cost model for the problem is defined as follows. The track bushel is drawn from bin J and bin K. The protein level of a track is the weighted average of 2 bins used for mixing, where alpha represents the mixing ratio. This equation here shows the revenue of each track going to an elevator J, which is a nonlinear function. And a single track profit is calculated by subtracting the total cost from the revenue. Finally, the objective is to find the best sequence of track that maximizes the overall profit. The model is subjected to the following constant. Mixing is restricted to 2 bins. Each track has a constant capacity it can carry. And for each for a single bean, bushel distributed in multiple tracks should be less than or equal to the initial capacity of the bean. So we collected our data set from a local Montana farmer who tracks the protein content of his wheat. The data set contains harvest information for the year 2016 and 17. The grain was distributed among 16 beans at different sites, and we have 3 elevators with premium dockage prices for selling wheat. For a fully loaded truck, the mixing cost ranges from $8 to $800, and the delivery cost ranges from $960 to $2,000. And the table here shows the statistics of the wheat distribution for the both year, where the first portion shows the bushel statistics and the second portion shows the wheat distribution. This table shows the elevator prices for different years. For each elevator, there is a base price for a base protein level. If a truck's protein level is higher than the base protein level, the base price increases following a step function, and vice versa if the truck protein level is lower than the base protein level. The figure here shows the cost function for elevator 3 in dataset 2017. The x-axis represents the protein level and the y-axis represents the price per bushel. As we can see, we have different step function for the premium curve and the dockage curve. For existing approaches, linear programming is used to solve the classical blending optimization problem. Blending is the process of mixing different quality raw materials to meet a specific target quality. However, the model only works with linear objective function and linear constants. Heike et al. Proposed a linear programming model to find optimal wheat blending for producing bread making flour. For our problem, the objective function is nonlinear and we do not have a specific target quality, which makes it challenging to model it only using linear programming. Mixed integer linear programming is often used to model real-world blending problems. They can provide both exact and approximate solution. Bilgan et al. Used MILP to optimize the wheat supply chain cost that includes blending, loading, transportation, and storage. For the blending, they used a specific blending plan from the domain experts. However, MILP is known to be NP complete and it is computationally expensive. Evolutionary algorithm has also been used in the literature for solving blending optimization problem. They can provide a fast approximation solution, which is often desirable by the users. Zhang et al. Proposed a hybrid evolutionary algorithm for solving the wheat blending problem in Australia. Their work closely relates to our problem. However, the problem formulation differs based on the US wheat market. Now I'm going to talk about the approaches that we use to solve the grain mixing problem. The first approach is no mixing, where we calculate the baseline profit without any bean mixing. The algorithm steps are as follows. For each bean, we load tracks separately until all the bushel of that bean are utilized. We take a partially filled truck in the solution. If it provides profit, that means the revenue is higher than the cost. If it's not, we discard the truck from the solution. Finally, we calculate the overall profit by summing up the individual profit from all loaded trucks. The table here shows the result of no mixing for the dataset 2017. Each row represents a truck entry. A bean number tells us from which bean the truck loads the grain. And load is the amount of bushel in truck, where the maximum capacity is 8,000. And the elevator tells us which elevator provides the highest profit. And by summing profit from all trucks, we get the overall profit. The second approach is called greedy mixing. Here first we create a lookup profit table by taking all bean pair and mixing ratio combination. We have 16 beans and there are 240 ways to select 2 beans. The order of the bean is important as the delivery cost only depends on the site of the second bean. And then we assume 9 discrete values for mixing ratio alpha, which gives us a total of 2160 track entries in the profit table. The table here shows how the lookup profit table looks like. Each row represents a track with a unique ID for each bean pair and mixing ratio combination. Protein is the average protein content of the track by mixing grain from the two beans. And the max profit is the maximum profit the truck can get when it's fully loaded, and the elevator tells us from which elevator the truck gets the maximum profit. And to generate a solution, we first sort the lookup profit table with respect to the truck's maximum profit. For each bean pair combination in the sorted lookup profit table, we load trucks fully or partially based on the mixing ratio if both bean pair has enough grain left to fill the truck, and if the partially filled truck provides a profit. Otherwise, we discard that combination and move to the next combination. Finally, we calculate the overall profit from each loaded truck. This table shows the result of greedy mixing also for the dataset 2017. Now for each truck, we have the bean pairs and mixing ratio used to fill the truck, bushels drawn from bean pair 1 and bean pair 2, the average protein level of the truck, and the elevator that provides the maximum profit. The last track entry shows that only bean 13 has grain left, and we take it separately without any mixing. And as you can see, greedy mixing increases profit by more than $4,000 compared to no mixing. The first evolutionary approach we proposed is the genetic algorithm. For the population representation, gene represents a track with the tuple track ID, bean pair, and mixing ratio alpha. The chromosome represents the list of candidate tracks to generate a solution, and the track ID in the chromosome is unique to ensure feasibility. For the initial population, an individual takes M random track entries from the lookup profit table, where M is a small subset of the whole lookup profit table. And the figure here shows the chromosome representation of an individual. And for the fitness function, we use the candidate track list to generate a feasible solution. First, we sort the candidate track list with respect to the maximum profit, assuming the track is fully loaded. Then for each bean pair combination, we load trucks fully or partially if both of the bean pair has available grain left. Otherwise, we discard it. And as the candidate track list is a small subset of the total bean pair combination, there might be missing combination for some of the beans. That's why we ran another loop where we load trucks if one of the bean pair has available grain left. Finally, we calculate the overall profit from each loaded truck. For the selection, we used tournament selection, and we also used elitism, where 20% of the fittest individual were moved to the next generation. The mutation operator swaps a single track entry with a random track entry from the lookup profit table, ensuring that there is no duplicate track ID. And for the crossover operator, we use the ordered crossover operator, which is a permutation-based crossover operator to ensure feasibility in offspring. This figure shows an example of the OX operator with a candidate track list of size 5. For a random crossover point, it first copies the gene of parents until the crossover point, and then copies the gene from the other parents if that track is not already present in the offspring chromosome. And this table shows the base solution that we got from the G algorithm for the 2017 dataset. The solution format is similar to the greedy approach. However, GA comes up with different bean pair combination to fill each track. And as we can see, the GA solution further improves the profit from greedy mixing and provides more than $10,000 profit increase from no mixing. Finally, we use differential evolution to solve the grain mixing problem. The population representation and the fitness function are the same as in the genetic algorithm. For the mutation operator, we use the code D best one. The standard D mutation operates in a continuous space for which we had to add up the mutation operator. We created the mutant vector by perturbing the chromosome of the generation-based individual. So in the equation, X represents the generation-based and AB represents two random individual in the population, and F represents the mutation factor, which we treated as a probability. So for a mutation value of 0.5, it means that with 50% probability, the mutant vector copies a gene from X based, and with 25% probability, it copies a gene from individual A, and with another 25%, it copies a gene from the individual B. And if the gene is already present in the mutant vector, it moves to the next index until it finds a valid track combination. For the crossover, we use the binomial crossover operator. We created the trial vector following this equation, where the CR represents the crossover rate. Again, to ensure feasibility, we move to the next index if the gene already exists in the trial vector. And for the selection, the current individual is replaced with the trial vector if the trial vector has a higher fitness. The table shows the best solution for the algorithm for the 2017 dataset. The profit obtained from DE is similar to GA. However, it also came up with different bin pair combination to load the trucks. And to further evaluate the performance of the algorithm, we created 12 additional dataset along with the 2 real dataset. Among them, we created 2 dataset by flipping the elevator prices for both years. And we created 10 artificial data set for the years 2016 and 17 by randomly varying the bushels and protein level in each bin. We also introduced a random algorithm to further assess the solution quality of the evolutionary algorithms. The random algorithm creates 100 random individual and returns the solution with the best profit. The GAD and random algorithm are stochastic, and the result here shows the average profit over 10 different runs. The profit is in thousands of dollars, and the bold values represents the highest profit for the data set. The underlying profit represents sufficient profit increase from the base profit, which we consider $5,000, as the protein tracking device costs in the range of $4,000 to $5,000. As we can see in the table, both GA and DE provided sufficient profit increase for all the real and artificial data set. And for most of the artificial data set, greedy mixing failed to provide a profit better than no mixing. And the figure here shows the convergence example of the GA and DA algorithm for the 2016 dataset. The red line represents the generation based, and the blue line represents the average population fitness per generation. The blue line in DA is a smooth curve, as DE always replaces a current individual with a better fit individual. So in conclusion, for all the data set, the evolutionary mixing provided a profit sufficient to cover the cost of the protein devices, and in many cases more than that. Therefore, the farmer should invest in the tracking infrastructure as long as the profit exceeds the amortized cost of infrastructure. For future work, we'd like to investigate the problem as MILP and compare it with our evolutionary approaches. We'd also like to analyze the computational complexity of the problem. And actually right now, we already have the NP hardness proof of the problem. And we would also like to see the impact in the solution quality for mixing more than 2 beans and using a continuous mixing ratio. Thank you all. And if you have any question, I'd be happy to answer them.
Thank you, Asad. Very interesting talk. Is there any question from the audience? Let me check. Maybe also you can write on the chat or raise your hand. Okay, I have anyway one question,
Yes.
Asad. Can you please go to slide 21? Because I'm not sure I have understood the representation, the genotypic representation you use. Okay,
Sorry. This one?
21, next one.
Sorry. Okay.
Yes, exactly, this one. Just to understand, in your representation, there are not only real values, but also that's a permutation because you use the ordered crossover. Is it correct?
Yes.
And the
So in here, like in time of the crossover, we only use the track ID as a
target.
like a
Okay.
permutation. And the next, like the tuple, it helps us to like assign bushels to the track based on the beans. So like the chromosome representation is like this, that helps us to calculate the fitness later. But for the crossover, like for the offspring generation, we actually like use the like unique track ID to ensure the feasibility.
I see. Now I see. Thank you. Is there any
Yeah.
question? If there is another question from the audience, I have a last one from myself. It's
Yeah, sure.
about the budget evaluation, the number, so I mean, determination criterion you adopted in your experiments. How many time or evaluations, I don't know.
So just to give you an example. Yeah, so if you see this figure, so we ran 500 iteration for the evolutionary approaches. And so for the termination criteria, if like the generation based fitness, if it didn't change for more than 100 iteration, we assume that the algorithm converts to a solution.
Okay, but in terms of minutes or seconds or hours, I don't know how many
Oh, the time?
time. Yeah.
Yeah, so if I recall correctly, in it takes like an hour or two to come up with a solution.
For one run. Okay.
Yeah.
I've got. Okay. Thank you, Asad.